All right, so today we're going to talk about circles. So you're probably very familiar with the term circle. If you're not, the definition of a circle is the set of all points that are the same distance away from a single point. And that distance is called the radius. So when you go from the center of a circle to the edge of the circle, that's the radius. The length from one side of the circle to another side of the circle, or 2 points on the circle, passing through the center, is called the diameter. Yes, ma'am?
Can I go get my pencil case?
Sure. So we've got diameter, we've got radius. Those are terms you should all already be familiar with. Some things that you might not be familiar with is a congruent circle. A congruent circle is a circle, yes. Okay. A congruent circle is a circle in which the radii are the same. So if I have two circles and they can be located anywhere on your paper or whatever, if their radii match, they are congruent circles. Okay, for example, if you put two pennies on the table, those pennies would represent congruent circles. By the way, if you put a quarter on the table and you put a penny exactly in the center of a quarter, then you have what's called a concentric circle. And concentric circles are when they share a center, but their radii are different. All right, so congruent circles are circles that have identical radii, but they don't have to share the same center. And concentric circles are circles that share the same center but have different radii. By the way, what can you tell me about circles and similarity?
They're all similar.
All circles are similar. Why?
Because they're circles.
Yeah. So there's only really one measurement we use to define what a circle is, and that's a radius. So if you just have one measurement, it's always going to be able to be comparable in a ratio to another one. So because there's only one measurement that defines the shape, they will always be similar to each other. Because everything else about the circle is proportional to its radius. All right. A new term that we need to pick up to be able to do what we're going to do today is the concept of a central angle. A central angle is an angle in which the vertex of the angle occupies the center of the circle. So if your vertex is the same as the center, you have a central angle. Makes sense. Central angle, center of the circle. All right, moving on. When you don't draw a complete circle, when you draw just part of a circle, that has a name. And that name is called an arc. And I'm not talking arc, A-R-K arc like the boat. I'm talking A-R-C arc like the part of the circle. So when I identify part of a circle, that's way too big. When I identify part of a circle, I usually have a way of describing the arc. And it's usually found by listing the two endpoints of the arc. So in this case, the green highlighted arc was in between points A and D. So it made a distance along the circle. Notice that the distance is not a straight line. It's an arc. And so it kind of goes in a curvy path. So this is one of the first times where we really started looking at distances and whatnot that aren't straight lines.
So would it be like R-A-D?
Yeah, I'm getting to that. So if I wanted to describe the pink line, what two letters do you think would be involved in that description? Right. So if I am going to describe the green line, I would just do a little arc mark over the letters AD. If I were going to describe the pink line, I would do an arc mark over the letters AC. So when I have an arc that is less than 180 degrees, which means it's less than half the distance around the circle, because 180 degrees is half of the circle, the entire circle is how many degrees? 360. So when I'm less than half of the distance around the circle, that is called a minor arc. And minor arcs always use 2 letters as the label. But did you notice that in dealing with the figure up here, if I make the pink arc really big, it uses the same 2 letters? The green arc and the pink arc both use the letters AD, don't they? How do we know which arc I'm talking about? Just by using the letters AD. Well, that brings into a concept called a major arc. A major arc is an arc that's bigger than 180 degrees. And a major arc needs a minimum of 3 letters to describe it. So if I just put the points A and D, I'm always going to go the shortest route between those 2 points. However, if I need to go the other direction, if I need to talk about this pink arc, then I need to start at A, and I need to include a letter that's not in the direction of D. So I could include either C or E, and now the first letter is where I start, the second letter is the direction I trace along the circle, and the last letter is where I end. So the pink arc could be described by ACD. What other letter combination could you use to describe the pink arc? AED. What about DCA? Or DEA? Either one of those are okay too. So a major arc has to have 3 letters. A minor arc will only have 2 letters. You never do a minor arc with 3 letters. You never do a major arc with 2 letters. There's one other combination that we haven't talked about yet. I talked about numbers less than 180 and numbers greater than 180. What's the other possible situation? Is 180. And those are called semicircles. Semicircles must also be defined with 3 letters. Why, you might ask? Well, I'll tell you. If I'm looking at a semicircle and I just use the letters DC, that means I could do that part of the circle, or I could do this part of the circle. So without a 3rd letter, I don't know which arc I'm talking about. So in this particular picture right here, if I wanted to go through and label 3 different types of arcs, I could pick a minor arc, and a minor arc would be like arc CE. I could pick a semicircle. Okay, so what was your question? Yes, there are infinitely many points that exist on the circle, so there are infinitely many different arc combinations. I chose CE as a minor arc, but if you were choosing it, AD would also be a minor arc. Can somebody give me another minor arc? DE? Somebody else? AC? So all of those are minor arcs. All right. If I were to do a semicircle, let's say I wanted the bottom half of this, my semicircle would be arc A, D, E. And if I wanted to label a major arc, let's say I wanted this distance right here, I would do arc A, D, C, or I could do arc A, E, C. Any questions about how to identify or label an arc? All right, here's what I want you to do. Here's a figure. I want you to pick one minor arc and label it. I want you to pick a semicircle and label it. And I want you to pick a major arc and label it. Your major arc must contain point Q. All right, just to recap, some examples of what a minor arc would be. Minor arc, there's several different ones. In this particular picture, I think the smallest one is arc PQ. And then a semicircle would have to be 3 letters. So arc PSR would definitely be a semicircle. And then here, a major arc, I think the biggest one would be arc PSQ. All right. So arcs have measures. And this is where we tie in the concept of the central angle. Okay? Remember, a central angle is an angle whose vertex is what? The center. So in this example at the top, you see how S is the vertex of angle RST? Okay, a arc measure is defined by being the same measure as the central angle that intercepts it. Intercept means that's where the sides of the angle cut off the circle. So if I trace the SR side of angle RST, it cuts off the circle at point R. If I trace the other side, it cuts off the point at T. So arc RT is intercepted by angle RST. Since RST has a measure of 50 degrees in angle form, then arc RT also is considered to have a measure of 50 degrees. Now, in this example up here at the top, they also find the measure of arc TQR. So TQR is the blue arc. But it didn't have a number to go with that, so how did they figure it out? Well, they know that the whole circle is 360, and the part of the arc that we don't want in the circle is 50 degrees. So 360 minus 50 is 310.
Wait, so the RT would just equal 50 because also doesn't matter anymore?
Right, so arc RT would equal 50 degrees for its measure. Arc TQR would equal 310 for its measure. And so the notation is the little m with an arc and the stuff that describes the arc. And that's how you designate its measure. Question?
No.
Okay. We also, do you remember how when we were doing segments, if we had 2 segments right next to each other, we could add them together and get the length of the big segment? And that was called segment addition. And if we had 2 angles right next to each other, we could add them together and get the whole big angle. Well, it works the same with arcs. If we have 2 arcs that are right next to each other, we can add them and get the whole big arc. So the measure of arc ABC, this whole red arc right here, can be found if you know the measure of AB and the measure of BC. You can just add them together to get ABC. So there is an arc addition postulate. All right, so to sum up, we've got ways of labeling arcs. We have found out their measure is based on the degree of the angle, the central angle that intercepts them, and so we have a way of classifying an arc's measure. Now we're going to forget all of that and talk about something completely different for a second. Well, actually, let's find some measures first. So in this one, the measure of arc BC, so here's arc BC, and this angle is what?
32.
So the measure of arc BC is 32 degrees. And then arc BD is going to combine the measure of arc BC with the measure of arc CD. So BC is 32, CD is 58. What happens when you add 32 plus 58? Yep, you get 90. So the measure of arc BD is 90. All right, now we're going to get a major arc here. Actually, this is a semicircle. Arc ABC is a semicircle. What do semicircles always have a measure of? 180 degrees. And then we're going to find the length, the measure of arc AB by taking 180 minus 32. Because ABC is 180, and I'm taking off BC, which is 32. So that'll leave me with 148. All right, does everybody understand how to find arc measures? Good, now I'm going to let you try it. Find the measure of these 4 arcs. All right, so what do we get for the measure of PR? Yep. The measure PR pretty easy. It's directly linked to the central angle 77. Really not a whole lot of figuring to do on that one. What about the RS arc? How'd you get 175? How'd you get 103? Yeah, I would have done 180, which is the semicircle, minus the part of the semicircle which we didn't use. And that's definitely 103. You should have helped your partner on that one. Yeah.
I was finishing the rest of it.
All right. So the measure of arc PRQ, what's that? PRQ would be what? I heard 208. How did you get that?
180 plus 28.
Yep. Semicircle is 180 plus another 28. What about the measure of PQR? PQR starts here and goes all the way around to R back here. I would have done 360 minus 77 because the whole circle is 360, but we don't go all the way around the whole circle. We are 77 short of it. So 360 minus 77, 283. Everybody okay with how to find arc measures? All right, now we're going to do something completely different. Ignore everything I just told you. We're going to talk about circumference. So what does circumference measure? The distance around the circle. So it measures the length of a piece of string if you stretched it around a circle. So here we have the circumference equaling 2 pi r. That's the formula I prefer to use because more often than not, it's really important to find out what the radius of a circle is. All right, so finding the circumference of a circle is a simple formula. And it's pretty easy. So you've probably already had the circumference formula in another math class. Let's take it to the next level. All right, let's talk about finding distance using circumference. Now remember, circumference is just going to measure how far around the circle you go. So what I've got here is I've got a 2-foot wide circular track. So to make a 2-foot wide circular track, what I would do is I would probably create a circle. And then I would create another circle that's 2 feet wider. By the way, these circles are, what kind of circles are these? No.
A quarter of a penny.
Yeah, those were concentric circles. And it's in the word problem. They form concentric circles. They share a center, but they don't have the same radius. Now, the inner circle has a radius of 8 feet. And the outer circle is how much longer? So this distance right here is 2. So what would the radius of the outer circle be? So radius O equals 10. Radius I equals 8. So that's the radius for the outer and the inner. Now, what the question I'm asking is the wheel on the camera out here is going to travel much further if it goes all the way out around this circle than the inside wheel will travel. That's amazing. They're the wheels attached to the same device, but one of the wheels moves a lot farther than the other one. It's going to wear out quicker. That's why if you drive a car and you always make right turns and never make any left turns, your outer wheel is traveling many, many miles more than your inner wheel, and it'll explode before your inner wheel does. So that's why they rotate your tires to try to balance all that out. You bunch of right-turning fools. All right, so we got radius is equal to 10, radius is equal to 8. What represents the distance all the way around the outside? The circumference. So I'm going to find the circumference of the outer, which is just 2 times pi times r, which is 2 pi 10, which I'm going to call 20 pi. What do you think the circumference of the inner is?
2 pi times
So it'll be 2 pi times 8. What does that come out to be?
16.
16 pi. Now, if I want to know how much bigger the 20 pi is than the 16 pi, what do I need to do?
Subtract.
Subtract. So that's going to be 4 pi, because that's 40. That's not 4 pi. Mr. Baker going cray-cray. All right, so 20 pi minus 16 pi is 4 pi. If I want to put that in the calculator, then 4 pi is 12.6. So if I wanted to find out how much further that outer wheel goes every time you go around the circle, it goes 12.6 feet about. Does that make sense? Just turn it into a subtraction problem. Solve it. All right, let's have you do one. I'll sketch it out for you. So we got a car that's, oh yeah, I told you we were going to have a car. So we got a car, that's not what I want to do. We have a car that's turning. And the outer wheel turns and travels a whole lot more than the inner wheel. So here's my concentric circles, and I forgot to mark the center. Let's just pretend it's here. So here would be the radius to one, and here would be the radius to the other. So according to the problem, the car has a turning radius of 16.1 feet. The distance between the two front tires is 4.7 feet. So let's say this is the outer tire, and this is the turning radius. I'm not sure whether the turning radius would be measured from the inside or the outside tire. I don't think it matters. So let's say it's from the inside tire. 16.1 will be the inside tire, and this is 4.7. So you tell me how much more the outer tire travels than the inner tire. All right, so by my calculations, the outer radius was 20.8. I added 4.7 to 16.1. The inner radius was 16.1. And the circumference of the outer was 130.7. The circumference of the inner was 101.2. And so that's going to leave me with 29.5 feet. So the outer wheel turns 29.5 feet more than the inner wheel. Everybody okay with that?
Wait, can you
Sure. All right, so now let's go back to all this arc stuff that we forgot about a few minutes ago. So here's where it gets a little confusing. We talked about the measure of the arc, and that's in what? If I'm measuring an arc, what was it in? We did a bunch of those. Yeah, it was in degrees. So an arc measures in degrees. However, there's also something called an arc length. And an arc length will be in units, like feet or something. So normally measurement and length used to be the same for our figures. In circles, it's a little bit different. Measurement means how big the degree is, and length means how long the string would be that you could fit over it. Finding the arc length uses a modification of the circumference formula. Because basically an arc is just part of a circle, right? So an arc length would be part of a circumference. And the key is just figuring out how much of a part of the circumference it is. So I'm going to show you how to do that. So the answer to that question is whatever the arc measure was, which is in degrees, over 360 will be some number less than 1. You're never going to have an arc measure that's more than 360 degrees, because once you get to 360, you're already around the circle. So your arc measure will be less than 360. That creates some sort of fraction that's less than 1, or part of the circle, and you multiply that by the circumference formula. So that whole degree over 360 tells you how much of the circle you're using in its length, and it gives you a number to multiply the circumference by so that you get the arc length and not the whole circle length. So let's see how that works out. So first of all, if I want to find the length of xy, I need to know the measure of xy. So what's the degree measure of xy? 90, because that central angle was a right angle, that's 90 degrees. That means the arc measure is 90 degrees. What's the radius of this circle? 16 is the diameter. What's the radius? 8. So I'm going to use the circumference formula, 2 pi r, but in this case that's 2 pi times 8. But I'm also going to use the measure of the arc over 360. So in this case, the measure of the arc was what?
90.
So 90 over 360 times 2 times pi times 8. And in this case, we're going to leave our answer in terms of pi. So I only want to multiply the numbers. 90 times 2 times 8 divided by 360.
So for the measure of an arc, you're always going to use that formula. Or for the arc length.
For the arc length, you're always going to use this formula. So 90 times 2 times 8 divided by 360 leaves me with 4. So the measure of that arc length is 4 pi inches. This one's a little bit different. We don't have the central angle measure. How do we determine how long this arc is? Or the measure of this arc? I got to be careful with my terms because how long means different than measure. Yeah.
360 minus 240.
Right. If the whole circle is 360 degrees, if we take 240 degrees away from 360, we're left with 120, which is the measure of that arc. So this angle right here was 360 minus 240. And that left me with 120. All right, so now it's 120 over 360 times the circumference. 2 pi, and what was the radius? 15. So you can just put all that into your calculator. We're going to leave in terms of pi. So what I would do is 120 times 15 times 2 divided by 360, and I get 10. So it's 10 pi centimeters. Everybody okay with that? All right, so we've talked about how to find arc measure. We've talked about how to find arc lengths. We've talked about circumference, and we've talked about central angles and how they relate to arcs in a circle. So let's find the length of a semicircle. What does semicircle tell you? It tells you measure. It tells you the measure. We want to find the length of an angle with a measure of 180 with a radius of 1.3. Leave your answer in terms of pi. And I'll go ahead and put the formula up for you. So it's the measure of the arc over 360 times 2 pi r. See if you can't find that and then check with your partner. All right, so what would the measure of a semicircle be? So that's going to be 180 over 360 times 2 times pi. What's the radius? 1.3. So I'm going to do 180 times 2 times 1.3 divided by 360 on my calculator, and that just comes to 1.3 pi. Remember, that's in meters. Everybody okay with that? All right. Here's your homework for tonight or the weekend. Enjoy.